Now, a very important concept in machine learning, and I'm going to cover concepts like this dispersed throughout the following sections instead of putting it all into one slide and boring you guys. But there are a lot of very important terms and concepts to be familiar about in machine learning, and I'm just gonna spread them out. For this section, we're gonna learn about overfitting and underfitting, or variance and bias. So this is something that you need to really watch out for when you're modeling on your data set. So overfitting means that you find a model, okay, that is so complex, so intricate, that it will fit the training data very well, almost completely accurately. So it'll go through every data point and it'll just, be perfect. The error will be like 0, okay, for your training data. And the problem with that is that it won't generalize well, right? When you bring in new data, all of a sudden, it's new data and your model was overfit to the training data set. So now new data is pretty foreign. It falls outside or far away from the model and where it's fit. And so it doesn't generalize well with new data at all. So this means that training error will be low because it fits so well to the training data, but validation or test errors will be higher. And essentially this overfitting means there's a high variance. So that's a more technical way of describing what's happening, high variance. So you want to minimize the variance. And so this is a very important thing to watch out for, because what might happen is you might, generate your family of models, you might fit your perfect, your good or the best fitted model, and you might test it your training data set, and you might find that the error is like nilch, right? It's like, it's very small and you're happy, you're ecstatic, like you found the perfect model. Yeah, you did find the perfect model to describe the training data set, but what you're trying to do is trying to find a general model that can accurately describe new data as well. So you can predict the new data. So you don't want it actually to be so accurate. You don't want to have a 99%, 100% accuracy on training data. That's why you should aim for 80% or something like that, because if it's too accurate on the training data, that means that now when you test it with new data, with a validation data set or a test data set, you're going to get a very high error. So you want to balance them out. You want to have the error that you're receiving from the training data set to be similar to the error you would receive from your testing data set. You don't want there to be high variance between these two error rates. Okay, you want them to be close to one another. Now, on the other side of overfitting, we have underfitting. So this means the model is too simple for the underlying pattern of data. It's way too general. And so the model will not fit the training data very well. This means that you'll have a very high training error as opposed to overfitting or high variance, in which your training error is high. But in this case, both the training error and the validation or test errors will be high, because your model is just crap, right? It's too general. And this type of model, the underfitted or the high biased, which is the more technical term for it, model, is also a model that does not generalize well. So they both don't generalize well, but they both don't generalize well for different reasons. So they're both a problem. You don't want to overfit or underfit. So you want to lower your variance and your bias. And so, yeah, this is a very important concept. If you're taking this course to study for any type of like test or, machine learning interview or whatever, this is definitely a concept that's going to come up. So I would advise you to like make note of this and to memorize these terms, high bias, high variance, because these are very important concepts for machine learning. Here's a very good example or a very good demonstration of what overfitting and underfitting is. So imagine that this is your data set, okay? So you have, it's a binary data set. You have two classes. So you have these class, which is represented by the green plus signs. And then you have this class, which is represented by red circles. And you want to find a model that most perfectly can predict for you the red circle versus the green plus sign. So you want to find this border essentially, right? You want to find this border. So whatever falls on this side of the border is the green cross, and whatever falls on the left side is the red circle. So if your fitted model, so you can generate a bunch of different lines, right? And you find the closest one. if the closest one, or like the fitted model, ends up being a line like this that runs straight through it, okay, it's not too bad, right? In general, the green pluses do fall on the right side of the line and the red circles do fall on the left side, but you have two green crosses here and you have 1.2 red circles on this side. So it's not too accurate. So it's too general, right? Like it doesn't account for this organic nature of the data, right? There's a very organic curve here and it does nothing at all to try and summarize that curve, right? It's just a straight line. Whereas the data set is not a straight line, right? There is no straight boundary. So this is an underfitted or a high biased model, okay? This right now, if you calculate the error, is very high for the training data set. And likewise, because it doesn't even work well on the training data set, obviously it's not going to work on the test data set as well. So the test data set's error will also be high. Whereas on the other end of the spectrum here, we have a line that perfectly describes the data set, right? This perfectly splits the data set into its two classes. There are no green plus signs on this side and no red circles on this side. So this is the perfect summarization for the data set we have on hand. But remember, the point of machine learning is to use our trained model to predict new data. So because this is so well fit to only the training data, it won't generalize well with new data. Because the only reason we have this bump in here, for example, is because of this particular data set. Maybe, right, there might be a red circle here as well that doesn't show up in the training data set, but, in future data, it might fit with like the more correct model, right? But we don't have a more correct model because we fit so closely to the training data. So this will have 0 training data set errors, but it'll have very high testing data set errors. So again, not the perfect model. So it is a perfect model for the training data set, but for all the data that's possible, it's not the perfect model. So here we have a more general model compared to this one, but it's more accurate, more precise, more complex than this one. So it's a nice, sweet middle ground. So there is error, right? This green plus sign does fall outside of the model. So there is definitely error, but it's smaller than this error here. And obviously it's greater than the 0 error here, but it's general enough to generalize with new data. So most probably the new data will also accurately be described with this model. So this is a good compromise, a good middle ground. It does have training data set error, but it's minimal and it will have testing data set error, and that will also be minimal, right? So think of it like this. This probably has like a 50% error for the training data set and 50% for the testing data set. This has 0% error for the training data set, but maybe 50% for the testing data set. This has probably like 80% error or 80% accuracy, let's say, for the training data set and 80% for the testing data set. So this is like 50% accuracy, 100% accuracy for the testing data set, 50% accuracy for the training data set, and this is 80-80. So you would rather have an 80-80 than to have like 150, because you can't do anything with a 50% accuracy on the testing data set. So take your time to really analyze and understand this picture. And this is another very good demonstration of what we call the bias variance trade-off. So you want to be in this upper left corner, right, where you have low bias and low variance. What happens when you have low bias but high variance is, look, in general, you are hitting the center, but your points, your hits are spread out. But if you have low variance, your points are clustered together, like your hits are very close together. But when you have high bias, it doesn't do you any good if they're all, your hits are close together. They're not, at the center. And then here you have high bias and high variance. So not only are your hits, not close together, but they're also away from the center, away from the target. So this is the worst place to be. So sometimes, right, based on your problem, you might actually prefer to have a high bias and a low variance. Like your goal might not be to hit one spot, but to, in general, for your hits to be close together. Or other problems might prompt you to search for models that have low bias and high variance. So you want most of your hits to be in a good central vicinity, but it doesn't really matter if they're close to one another. So this is a very important trade-off to be aware of. So how do you quantify distance? Remember, distance is needed to assess which of the models in your family of models is closest to your actual data set. So you need a way to quantify the distance between the data and a model, any model, mathematical model. One option is to find the vertical distance between each point and the model. So a prediction is the y values given to the model, okay? And the response is the actual y values in the data. So because the prediction is supposed to be a more general, more simple summary of the data, it's not going to, the y values or the prediction are most of the time not going to be the same as the y values for the data, but they should be as close as possible. So the distance is the difference between the prediction and the response. And the overall distance is a metric that will help you collapse all the individual distances into a single number. And so, there are different ways of doing that. Most commonly, we use a method called root mean squared deviation. So you get the distances between all the individual points of the prediction and the response, and then you plug it into this root mean squared deviation formula, and it collapses it all down into a single number. And the bigger the number, the farther away or the less accurate of a description the model is, and the smaller the number, the more accurate it is. So you want to try to minimize this number to find your fitted model. And my references for, most of these slides are just from me, but in the next video, I'm going to be using some stuff from the R4DS book to show you how to do this practically in R. So I would definitely advise you to check out this book if you already haven't, and more specifically the Model Basics chapter, where it will go over how to build a regression model from scratch. And I'm going to be showing you how in the next video. See you then. Bye-bye.